You had time to think a little bit about what Line talked about during the morning session. And Line had actually made a very good introduction of what Giacomo is going to talk about. So actually, this is a nice continuation. So after a rigorous procedure yesterday, 3 hours going through the posters and your voting, Giacomo was awarded the second prize for the best poster award. So please come here, Giacomo, and warm congratulations. So now we are actually happy to listen to your talk about topological actions in AC/DC grids with large penetrations of renewables. The talk is going to be about 15 or maximum 20 minutes, and then there will be also room for questions. Yep. So.
Okay, now you should be able to hear me. Okay. Okay, I will tremble a bit. You know, you're a lot of people. Okay. Thanks, Spiros, for the introduction. Thanks, DTU, for organizing the summer school, and also to Lina for not putting pressure on me during a 3 hours lecture. Today, I will talk about, topological actions, as she mentioned before, but for AC/DC grids. So here we are adding DC grids. We are in Europe, and we take into account a large penetration of renewables, mainly offshore wind. It's a project funded by Direction. Yeah, it's a Directions project funded by Belgium, and we collaborate with Elia, the Belgian TSO. So the outline of the presentation, we have 5 sections: introduction, motivation, models, results, and then some take-homes. I will also show some figures because I think it's interesting to see what has been done in Europe for offshore grids. So starting from the introduction and give a bit of numbers. The European Commission wants to put 450 gigawatt of offshore wind by 2050. It's a huge number. There will be a lot of cables. And in the North Sea, we aim to have a 300 gigawatt of offshore wind by 2050. There was a report from ENTSO-E that computed that we need 22 gigawatt per year installed offshore wind in the North Sea to reach this target, while in the last 10 years we had 2.5 gigawatt. So you see, it's almost 10 times more per year. But also, in order to bring all that offshore wind to shore, we need more grids. And in this sense, the European Commission said that we need 600 billion euros to build all this grid. And again, and so we computed that we need 14% of this. They call it dual purpose hybrid infrastructure. They might have forgotten to consider the onshore grid in their simulation, and actually it might be way more. The motivation, so behind my work, you can see it here. Can we optimize the topology on an hourly basis to counteract the variability of renewables? And how do we integrate this in steady state OPF simulation to validate optimum power flow models? We also have 2 more questions that, they keep me awake at night, and it's how to maximize how do we put all these renewables offshore, onshore, and do we have enough workforce and willingness to do this? Yeah, also the light keeps me awake at night here, but, but this presentation was the main reason this time. I also put some possible solutions that we have. So as you can see, we know the solutions. They are offshore wind, among the others. They are offshore substations. It's interesting that these offshore substations are 44,000 tons and 106 meters times 77 times 90. It's a big one. And as you can see, it was done at last year. They said that by 2031 they want 14 of these ones, just for the Netherlands, just for their ideas. So we know that there are these possible solutions. We know that there are some constraints that I liked. Yeah, I liked. Didn't like that much, but yeah, I put there. Climate change, reliability issues, public acceptance for the non-Belgian people in the room. They struggled to build a transmission line for 10 years in Belgium. It's called Ventilus. So now they wanted to put it underground, and that's why also my supervisor, Dirk van Aertem, got quite a decent funding to do that. So if you want to join our research group, please. Yeah. Dirk, if you will ever hear this, say thanks. But also, we have a sense of urgency for climate change. This is my hometown last week, 30 centimeters of water in my basement because of, yeah, it rained for 2 hours. So we wanted to do this by putting offshore wind. You see a car here. This is a boat for our, yeah, just the rotor, and then the blades for offshore wind. But also we wanted to do it with cables, and especially HVDC cables. Here you see the arm of a converter that is normally put offshore, 12 meters. There are 6 converters for each of the substation that you can see here. So it's a lot of stuff, right? So we wanted to just, yeah, this was a big overview on what they are doing on offshore grids. What we proposed was first optimal transmission switching for AC/DC grids. So to translate what I just shown in mathematics terms, they already do it in Europe. They would like at least to start doing a bit more. You can actually check all these links for what is done on an hourly basis in this region, core capacity calculation region. While I was preparing the slides this morning from 5, 6 a.m., you see that there were some phase shifting transformers that were changed here at Thailand that was opened. So actually these things are done, but they are not done that much, and they are mainly done in a preventive action, but we can improve it, especially on the DC part and especially with a lot of renewables coming into the system. And you can actually check it for every hour. I'm just giving some references because it's extremely interesting and I think people should know about this. So going back to optimal transmission switching, there's this paradox that adding a road does not always lead to reduce the total travel time for people. It's for logistics, it's for traffic, but it can be also for power systems. As Line showed before, actually, you can switch on and switch off lines, and that's what we did. So here we have a full AC/DC OPF formulation. It's nonlinear, non-convex, and PR'd. What we did is for the DC grid, adding binary variables, and you can decide whether to switch on or off also DC lines and DC converters. This just helps us to model the DC grid. It's not such innovative, but nobody did it before. But what really is the contribution of my work is busbar splitting. So there was a formulation from Morsi et al. That essentially they take each one busbar. You can give the chance to split it through a tie line that is zero impedance line. It's a switch essentially. And then each grid element can be connected to either one or the other part of the split busbar through an auxiliary variable. That is a binary variable in this case. Then you run an optimization problem, and then you can modify the topology. This is what was in the literature. There are 2 papers about this, and that's it. What we did, we took this idea and we modeled it through a switch. It's a switch, but it can be also referred as this connector, as a DC circuit breaker, as a AC circuit breaker. It just depends on the constraints you add. Now we just consider it as a switch because it's for 1 hour we can just optimize the grid topology. And you see for the AC you have variables that were mentioned before, voltage angles, voltage magnitudes. For the DC grid you don't have reactive power, you have only voltage magnitudes. This is essentially what we did for the switches. As said, you can implement the constraints to model the current that goes through this. So actually, if you open it, you can compute the overcurrent. And if the overcurrent is too high, then you say, no, we cannot switch this. And as you see, the formulation as a binary variable time a linear, yeah, just normal decision variables. Binary variable, decision variable is a bilinear term that Line reformulated as a big M reformulation. We also did that, but we also kept this formulation to check whether these bilinear terms were so bad to optimize. And we did it, as said, for the AC and DC grid. It's a bit complex, but I have some animation, I believe. So let's say we take this load and we want to connect it to either one or the other split busbar. We have these switches in order to do that, and the same we can do for this generator, one or the other busbar. Same for DC grid, that is a DC branch we connect it to either one or the other part of the bus bar. And we give it to the optimizer, and we see what's the result. We tested this on 3 main test cases, 5, 39, and 67 buses. This is a multi-terminal AC-DC grid from PGLib. I shown here power models, because power models was developed by the speaker tomorrow, Carton Coughlin. My supervisor, Professor Akan Ergun, co-supervisor, developed the power models AC-DC part. For the OTS, you see that actually there's an OPF result, AC OPF 194.139. When we do AC OTS, we actually have a reduction in objective value and 3 lines are open. So, okay, what Lina showed. For 39 AC-DC, we actually see that we have 4 AC lines, 4 DC lines, and 7 DC converters that are opened. So by switching off DC branches and DC converters, we achieved a lower generation cost. This is one of the first findings. For busbar splitting, we decided to switch busbar 2 here because there was a congested line. And we simulated it through the formulation with bilinear terms, reformulation with big M, and then SOC, QC relaxations, and LPAC approximations. And as you can see, it's feasible for the AC and also for the reformulated version. For the reformulated version, it took more time, but it reached a better value, essentially because it's a bit less complex, and probably here the optimizer got stuck in a local optimum. So we have AC feasibility and better result than the AC OPF for a decent time still. Then for the SOC and QC relaxation, there might still some bugs in the formulation, but we got a AC feasible result, but it's the same as the AC OPF. So basically, we haven't achieved a better solution. For the LPAC formulation, that is linear but with reactive power, we actually achieved a AC feasible result with lower result compared, lower objective value compared to the AC OPF in 0.068 seconds. That is something we were, I was pretty happy with. And we did the same, for example, with the 2 busbars. And here we see that you essentially open, you split the busbar, and you connect the grid elements a bit wherever you want, and you actually achieve better results, again, compared to the AC OPF. So how are we going to implement this in real life? Because then, as engineers or as a researcher, we want also our ideas to be just translated to the real life. Belgium came up with this idea that was mentioned yesterday by Spiros as well. In Denmark, they are doing the same. So building an energy island that is looking like this. So this one is a render, but essentially you wanted to put these big concrete blocks or caissons in the North Sea, and then build electrical infrastructure based on that, both AC and DC, and then operate the DC grid with this busbar splitting. If you're interested in the project, there's here a link for the Princess Elizabeth Energy Island. And it looks a bit like this. So there will be 3.5 gigawatt of offshore wind coming to this energy island. You have a AC-DC converter, and here the DC grid. Here you have the switch, that is what was modeled with the busbar splitting, but also you can do it here, and you can decouple AC and DC parts of the energy island. And in the case of Belgium, there will be a 2 gigawatt link coming to the onshore grid, but also 6 400 megawatt lines coming to the onshore grid as well in the same substation that can be splitted theoretically. Then they will connect this to the Danish energy island, and then also to the UK. But I know also only for Belgium for now. So the take-homes and conclusion for this presentation is that we achieved a reduction in generation cost by only performing the topological actions, both optimal transmission switching and busbar splitting. We didn't have any n-1 criterion, n-1 or n-1 x, as it was mentioned yesterday. And we think that we also need a bit more AC/DC test cases to evaluate these methodologies, because, yeah, it's pretty difficult to find cases for OPFs, and you know, these models are a bit new, so we need. Yeah, I'm going to work a bit in that direction. And also, as mentioned before, we developed these switch models, but we can also refine them with further constraints, just to try to check whether, for example, a converter is stable, or we wanted to model different types of AC and DC protections. I think I said almost everything. In the rest of my work, I will also refine the model with CVAR optimization that was mentioned yesterday, and probably it's really interesting to consider faults that can happen. Unit commitment constraints, we wanted to overload the DC lines, unbalanced operation, and all the things that you see listed here. So I thank you for your attention. If you wanted to connect with me on LinkedIn, here is the QR code. And also, yeah, it's a bit of advertisement for me. I'm the chair of SIGRE Belgium NGN and the IEEE chapter of Leuven. If you're interested in our activity or you wanted to come and give a talk, you can scan the QR code, follow the page, and send me a message or an email. I think I'm still in time. It's 15 minutes. So yeah, thank you for listening to me. I'm happy to answer to your questions.
Great, thanks a lot, Giacomo. So, questions? Yeah, Rodrigo.
Giacomo, very nice presentation. Congratulations.
Thanks.
Regarding algorithms to solve this massive problem, have you seen anything? Because it seems like it's a very heavy, complex problem. And if you want to add a lot of other components which will add on binary or integer variables, this could be very challenging. So have you thought about algorithms to start solving these problems?
Yeah, thanks for the question. We thought a bit in that direction. So we developed a full AC model. So based on the AC OPF, all the constraints. And this is a MINLP, NPR complex problem, non-convex. So in that case, we tried to see what happens, and as shown, we reach some results. It's high computational time, but we know that they are optimal results. We implemented the three reformulation, 2 convex relaxations that are the QC and the SOC as shown, and the LPAC that is essentially linear. And we saw that with those formulation, actually, you might reach not as good solution as the full MINLP problem, but still a solution that is AC feasible. That is also what Lina was looking at in her presentation. So yeah, we reformulated a bit the problem around. We also tried to make the binary variables continuous, and then try different starting points, or trying to, based on the results, assign the variables a starting point and then solve the problem. You can do it still, but we need to work further to develop the models more. I don't know if it answered a bit.
Just probably explain myself very badly, sorry. You answered the question, but I really wanted to ask about decomposition algorithms, or something that which is not exactly reformulating the problem in order to make it more tractable, but as I said, a decomposition algorithm or any other algorithm that will help you to deal with the problem, with the large-scale problem.
So in the past, I worked with Danzig-Wolf decomposition, as you had the paper. I read that paper quite a few times when implementing that. It wasn't performing extremely well for the OPF, but it was really work that I did in my first year after graduating, so I wasn't really sure whether it was implemented the best. Benders decomposition is something that we thought of, but yeah, those are just ideas for now. We thought about the DOPF and yeah, just this relaxation more. Yeah, so there's for sure room to also check those things. I'm not sure whether they make necessarily sense for this case, but yeah, I'm happy to talk about them later if you want. Okay, thanks.
Okay, next, Lina.
Yeah, thanks, Giacomo. I had a question. It's very nice to see this again. A nice poster yesterday, so congratulations. I had a question about. So you're saying you're looking for other test cases,
yep.
right? How complex do you expect, in particular, the DC grid to become? And like, what kind of test cases? I mean, where will this be? Kind of a DC grid be? Where do you see that as being important? And kind of what sort of test cases would that reflect?
I mean, it's important in the sense that for sure there will be more DC connections in the North Sea, and they will be interconnected. So we expect the multi-terminal links, but maybe I forgot to mention that these links are also high power, right? So it's not in terms of branches that or links that we will have a high number, but in terms of the risk and the consequence of failure of one of these lines that we wanted to study them. And in order to do that, the test cases might become bigger because we wanted to amplify the AC parts. So then we attach bigger grids to the terminals, like in Europe. And then the DC grid we expected to reach, I mean, if Tenet, instead of putting just point-to-point links, puts a grid, then there will be, I will say, tens of lines. So it will become a challenge, probably. And within my project, we got some data from Elia. But we are working towards using that data, but also thinking about modularity in this sense. So also evaluate investments that can be made in the future. So yeah, I don't know if it answers the question.
Yeah, no, thanks. I was just curious.
Thanks.
Other questions? So I also maybe have one or two. Okay. So my first question has to do, what is the added complexity when you add the DC grid? Have you tried to quantify that? I'm not sure if it's possible to quantify, but so you just have the AC grid and you do the busbar splitting and the topology optimization, right? When you add DC nodes, how much more complex does it become in terms of time, computation time, or solution?
Yeah, it's. I wouldn't say it's like adding AC buses because you have the converter, and if you wanted to fully model the converter, then it's a lot of equations. So you model each part of the converter differently. So I would say probably in terms of 20% more time overall. But then maybe the additional complexity here is using our engineering knowledge and saying, okay, we wanted to split the busbar, but we know that if we don't have a DC circuit breaker, but we have just a disconnector, then we need to bring the power down to 0, open, and then bring the power up. And if you have 6 gigawatt, then that may create a problem on the onshore grid of Europe. So also model this with like reserves to prepare such a thing. It's something that we are investigating in the Directions project, and I think it might be relevant. So, but this would add the complexity, right? Because then you add the time series, you add also the load series.
It's time dependency after that, right? And then you have actually to do a multi-period, maybe a kind of optimization.
Yeah, exactly.
To do that. Okay, that's very interesting.
Okay, thanks.
Any other questions? Then thank you very much, Giacomo.
Okay, thanks.